Next part of this chapter is about the other types of the diode. We have a lot of diodes. This is a regular one. This is a regular one. Another one is called the Zener diode. This is a Zener diode B. Schottky diode, also this one here. We have a varactor. We have the LED and the photodiode, which are opposite to each other. One of them, actually, when you give them energy, it will give you light. The other one, when you give it light, it will give you energy. So, as you see from the symbol, it's clear that this one, for example, is what you have. If you have a current in the diode, it will give you light here. It is emitting light. That's why we call it LED, light emitting diode. The other one, if you have light, it absorbs this light and create current. So this is a photodiode. So let us see what's the Zener diode. The Zener diode is very similar to the diode, regular diode. The only difference that it actually, when in the reverse mode, it has a certain voltage. Okay, it's not a breakdown voltage like in the regular diode. So, for example, if you look at this one here, in the reverse, voltage here is called, for example, 5.1 volt. So this means in the reverse mode, it is a voltage across this diode is 5.1 volt. If it is less than 5.1, if the voltage is less than 5.1, it will act as open circuit. But after that, if it is more than 5.1, it will act as just regulator. It will stop the voltage at 5.1 volt. Okay, so imagine that the voltage here, this voltage, for example, here, this circuit, this is a 9 volt now. Assume that it is not 9 volt. It is reverse mode because this positive is connected to the negative, so it is reverse mode. So imagine that this voltage is not 9 volt. It is 1 volt. And this Zener diode, the voltage, the reverse voltage is 5.1 volt. So if this one is 1 volt, then in this case, it is less than 5.1, then this Zener diode is acting as open circuit. Okay, it's open circuit. Make it 2 volt. Make this 2 volt, still open circuit. 3 volt, open circuit. 4 volt, open circuit. 5 volt, open circuit. Okay, 6 volt, now it is more than 5.1, right? So the voltage across this Zener diode will be 5.1. Why? Because the voltage is more than the reverse voltage, which is 5.1. Make 7 volt, would be 5.1. 8 volt, 5.1. 9 volt, 10 volt, 20 volt would be 5.1. Okay, so this is the difference between this diode and the previous one, Zener diode and the regular diode. The regular diode is open circuit. I know that it's open circuit in the reverse mode. Okay, but here, no, it is open circuit until it reaches this value here, 5.1. If it is more than 5.1, then the voltage will be will be constant, 5.1. So, for example, if we have this circuit here, if I want to calculate the current, this I. So I know, since this one is 9 volt, then the voltage across the Zener diode is 5.1 volt. 5.1 volt. Okay, so now what is the current? The current in the resistor will be here. This 9 volt, will 5.1 of them will be dropped on the Zener diode, and then the remaining will be dropped on the 3K. Then the voltage across the 3.3K is 9 volt minus 5.1. Okay, this is a voltage. Divided by the resistance will give you the current. If the voltage here is 20, for example, 20 volt. Then now what is the current here? This 20 volt will be divided by here and here. So it will be the voltage across the 3.3K will be 20 volt minus 5.1 and so on. So the constant says the current here is 5, the voltage here will be always 5.1. Assume that the voltage here is not 9 volt, is 3 volt. So now what is the voltage across the resistance? The resistor here. Okay, in this case, the voltage across the Zener will be this 3 volt. Will be open circuit. This one will be open circuit. So you don't have any current. You don't have any current. So in this case, you do not have a current in the resistor. Then there's no voltage. If the voltage here is 4 volt, for example, then again the Zener diode is open, then you don't have any current, and so on. Okay, so this is how you calculate the voltage if you have a Zener diode. If the voltage is more than the reverse voltage is more than the reverse voltage for the Zener diode, then it will make the voltage 5.1, for example. Here is 5.1. If the voltage here is less than 5.1, the Zener diode will be open circuit. So let's see here in P2 Spice, how does this using P2 Spice, this circuit here. So we have a source that is 20 sine omega t. And this is a 1K resistor, and this is 1K resistor. Okay, so what happened here is that this voltage will be a sine wave. It look like this, as the maximum is 20. Then will go down to be negative 20. So like this. Okay, so now the Zener diode will be sometimes in the reverse mode, sometimes in the forward mode. If the voltage is positive, if this is positive like this, okay, so in this case will be in the reverse mode, because now the positive, if this is positive, positive will be connected to the negative, then this is the reverse mode. So if the voltage is positive here, so in the first half, which is positive, the Zener diode will be in the reverse mode. So what happened? That the voltage across the diode, okay, the diode will be considered open circuit, okay, until the voltage will be reached 5.1 volt. If we don't have this Zener diode, this means this 20 will be divided equally between 1 and 1. Then the voltage is assumed to be a sine wave like this, with maximum 10. The voltage across the 1K, this R2, is supposed to be 10 sine omega t, like this, 10 sine. Okay, so when the voltage between 0 and 5.1, the Zener diode will be open circuit. Why? Because the voltage across the Zener is less than 5.1. Again, this 20 sine omega t, okay, divided between two resistors. Then the voltage across R2 is half of 20 sine omega t, will be 10 sine omega t. It should look like this. Sine with maximum 10. Okay. Then when the voltage 10 sine omega t, of course, will rise from 0 to 10 and go back. When the voltage is from 0 to 5.1, okay, the voltage is less than Zener reverse diode, reverse voltage. Then the Zener will be open circuit. You do not have Zener. Zener is just open circuit. Then the voltage will look like this. You don't have Zener at all. But if the voltage is more than 5.1, then it will clip the voltage. It cannot go more than 5.1. Then the voltage will be 5.1 across the Zener, because the voltage across the Zener and R1 are the R2 are the same. Then the voltage across the Zener will be 5.1 volt. Then after that, when it becomes less than 5.1, it will be open circuit again. So here is open circuit in these two periods, this one and this one. It's open circuit. Here, the voltage is a Zener diode reverse voltage. And the other side, when the voltage is negative, negative will be connected to negative, then this is a forward bias. Then it will act as a regular diode. Then it will be short circuit. Okay, so this is a short circuit. So you do not have a voltage across the resistor, or it will be 0.7 volt, 0.7 volt for the silicon. Then the voltage here is 0.7 volt, like this. Okay, so, or ideally supposed to be 0. Short circuit, then there is no voltage across R2. If you talked about ideally, then this one is 0 volt, short circuit. Okay, so this is for this problem. If we exchange this, if we reverse it, then what happened? What happened is that you see here, when you have this positive voltage, the input is positive. If this positive and positive will be forward bias. So forward bias, this means that this is short circuit. If this short circuit, then you don't have a voltage here. Okay, because you are shorting the resistance, the resistor. So you don't have any voltage. Okay, so that's why the voltage is almost zero, but because we know that the forward bias, the voltage is 0.7 for silicon, then it is 0.7. So here it is 0.7 volt. And when the voltage is negative, the source is negative, then this will be negative, this one is positive, then it is reverse bias. Then in this case, the zener will regulate the voltage at its reverse bias voltage, which is 5.1 volt. Then when the voltage is less than this 5.1, it will be open circuit here and here. And when it is more than 5.1, absolute value, of course, it will stop it at 5.1, like this. Then this is a Zener diode. If you have two Zener diodes, if you have one like this and another one here, then in this case, you will have one of them, for example, will be short and one will be regulator, for example. So in this case, you have actually, it will be always short and so on. What about the LED? LED or light emitting diode. As I said, from the name or from the symbol, yeah, if you have a current in this diode, if you have a current, so this means that if it is forward bias, if you have a current, it will emit light. And this light could be yellow, could be red, could be blue, could be green, and so on. Okay, so this is the LED. So LED is a diode that produces light with electric input, and so this one actually is producing light, as I said. It will radiate light. And the difference between this diode and the other regular diode is only that first it will produce light. Second, its forward voltage is different. It's not 0.7. It is always higher than 0.7. For the red, for example, it is 1.8 volt. So this is the lowest one. And for any other color, it is it's higher than 1.8. Every light, every color has forward bias. So for the red is 1.8. For the yellow is different. For blue, for green, and so on. This is the only difference. But the concept is the same. So as I said, the only difference here for the LED is that it will give you light. So this is what to use, for example, in some devices like in some circuits. You need to have a light, for example, if you have power. Okay, this is LED. This is example of LED. So this is just a regular diode, as I said. Okay, the only difference is this voltage here. For example, here is 2.1 volt. For the silicon, it is 0.7. So if I want to calculate the current, what is the current here? The current will be, for example, here, this is 5 volt, 5 volt minus 2.1 dropped on the diode. So it will be 2.9 volt divided by the resistance, which is R. Okay. So here, if this R here is potentiometer, so R is variable. You are rotating it. So you have this R, for example, 1 ohm, 2 ohm, 3 ohm. You are changing it, potentiometer, variable. Of course, this case, if your R is small, you have a higher current. If R is high, you have a smaller current. Then you can control the light. Okay, so you can control this light. Okay, so the brightness of this LED controlled by this light. If you have two LEDs like this, D1 and D2, then what happens if this, for example, this one is a sine wave? Then if you have a positive, like this, positive wave, what happens? This one will be forward, and this one will be reverse. This one is forward, and this one is reverse. So if you have in the first one here, first half, D1 is on, and this one is open. So this one will work, will light. This one will not light. If Vn is negative, then in this case D2 will be forward and D1 will be reverse. So this one will be on, this one will be off. So what happened here? Assume that you have a sine wave with low frequency. You don't want high frequency to be able to see. So assume that D1 is yellow and D2 is red, for example. In this case, you will find the light will change like this: red, yellow, red, yellow, red, yellow, red, yellow, and so on. Okay, depending on the frequency, of course. So if you have very low frequency, Vn is 1 hertz, for example, then you will see the lights. You can try this. So you have the light. This one will be on, this one off, and then this one's on, and this one's off. The second or the next one is a photodiode. The photodiode is the one that that we use this for the solar cells. You have it in the sun. It will absorb the light, the sunlight, and then create a current. So can store it and so on. And there are two types of photodiodes. One is called photovoltaic, and the other one is photoconductive. The first one doesn't have. You don't have to connect to voltage to work. You don't have to do it like this. So it doesn't have to have a voltage circuit or source to work. But the other one, so that's why you call it here. It can be used as a solar cell. Of course, when you have one in the front yard or backyard, this is the one that we call it here photovoltaic. So you don't have to connect it to any source. The other one is called photoconductive, and this required reverse bias to work. Reverse bias to work. But this one is acting as a current source, but its response is faster than the previous one, than the photovoltaic mode. Okay. So, but of course, there's a noise and dark current are worse. Yeah? So this one does not produce high current in the dark. So the first one is important, of course, because when you have it the whole day. It will absorb the light and then produce current at night. This is its job. But the other one has a higher response, but it is not. Its job is not to produce current in the dark. There are other diodes here. One is called Schottky diode and varactor diode. Schottky diode. This is a symbol for Schottky diode, and this one here you don't have PN junction. It is PN is a semiconductor. You have a P type and N type. This one has a metal, so you have a metal inside it. So it's semiconductor and metal. And the reason for when we do that, we have two advantages. One of them is that it is very fast, and the response is very fast. When we have a switch in, if you want to switch on and off, it is very fast, faster than the regular one. And also the forward voltage is lower. It's not 0.7, for example. It is 0.2 to 0.3. So these are the two advantages of the Schottky diode. For the varactor diode is very important because the varactor diode is acting as a variable capacitor. When you have a voltage across this, especially the reverse voltage. So, for example, the reverse voltage, you change it from 2 volts, 3 volt, 4 volt, 5 volt. In this case, the varactor diode is acting as a variable capacitor. So, for example, 1 microfarad, 2 microfarad, 3 microfarad as a function of the reverse voltage, which has a lot of applications. A lot of application, because if you assume that you have this in a circuit, then in this case you can change the resonant frequency, for example.